Hello everyone, this is Reem Haweel. I'll be presenting our research entitled by a novel framework for grading autism severity using task-based fMRI. This is our presentation outline. So what is autism? Autism spectrum disorder, or the ASD, is a neurodevelopmental disorder characterized by different symptoms of reduced ability in language, social, repetitive, and communicative behavior. According to the CDC, 1 out of every 68 children in the United States has autism. The autism spectrum includes a range of different grades. So the research question is, can machine learning help in determining the status of the children on the autism spectrum? Currently, the gold standard on autism diagnosis is the Autism Diagnostic Observation Schedule, or the ADOS. The ADOS interviews assign a score indicating the level of severity for each individual. Brain image modalities and machine learning are being investigated for the development of objective technologies for early ASD diagnosis. One of these brain image modalities is the task-based fMRI, which is commonly used in all brain regions to answer evoked blood oxygen-dependent signals, or the BOLD signals, in response to certain tasks. The state-of-the-art in ASD diagnosis using task-based fMRI is limited. These are the most recent research. They included a dataset of limited number of subjects. These subjects underwent different tasks during the fMRI scan. There were some common limitations in the state-of-the-art. First, the focus of previous studies was to analyze or diagnose autism disorder in two groups of ASD, or typically developed, which is not sufficient for addressing differences among subjects across the wide autism spectrum. Moreover, while relatively high age ranges in these studies, it is important to include toddlers into any new study aiming for early detection of autism. So what drives our motivation is that ASD is diagnosed at the age of 3, but some characteristics can be noticed as early as 12 months old, especially with the progress of medical imaging and the latest state-of-the-art machine learning approaches. Also, alterations in the functional activity is believed to be important in explaining autism causative factors. Although task-based fMRI provides indicative information about brain functionality impairment and biomarkers, only few attempts for classification using task-based fMRI were recorded in literature. So the goal of this paper is early detection of ASD by developing more specialized objective computer-aided diagnosis that utilizes brain processing and analysis tools as well as machine learning algorithms at an early age. The second goal is developing autism severity grading approach to diagnose each autistic subject as mild, moderate, or severe autistic. Finally, we investigate the best performing classifiers to grade ASD subjects based on the task-based fMRI by also choosing the best representing features. In order to divide the subjects into 3 groups, we have used the calibrated severity scores from the ADOS reports, and they are divided into 3 classes. Subjects who have the CSS from 1 to 4 are mild, others who have the CSS from 5 to 7 are moderate, and the rest who have the CSS from 8 to 10 are severe. We have included 39 subjects, 13 subjects per class, with the young ages from 12 to 27 months. The mean age is 20.13 and the standard deviation is 5.07 months. The data is downloaded from the NDAR site and they are a task-based fMRI data. The images were recorded in a response-to-speech experiment that included 4 audio stimuli: silence, complex forward speech, simple forward speech, and simple backward speech. They are alternating repeatedly along 6 minutes and 20 seconds. This is our proposed framework. First, we input our data, which is task-based fMRI volumes. Then we apply pre-processing using FSL. The second step is feature extraction using GLM. Extraction of the bold signal and GLM modeling are performed using FSL. For each brain voxel, we apply the GLM modeling on the observed bold signal, which yields different statistical and analytical values that will be used for feature extraction for each brain area. More details will be provided for that step later in the presentation. The third step is classification and grading using recursive feature elimination and random forest. The final output is the grade of the autism severity, whether it's mild, moderate, or severe. This is a more detailed explanation of the second step in our framework, which is feature extraction using GLM. The output of the pre-processing step is a bold signal for each brain voxel. Our goal is to represent the level of activation of each brain voxel in response to each task. That's what the GLM provides. So, we apply GLM on the bold signal of each voxel. The output is a regressor or beta value for each task in each voxel. We have 3 audio stimuli, which are represented by 3 regressors, which represent how similar the bold signal is to the hemodynamic signal. We also calculate the average beta for them. In order to get a more indicative value, a z-statistic value for each regressor are calculated to indicate the level of significance. Now we have thousands of voxels. Each voxel has 8 values. How to reduce this number of features? So we applied brain parcellation using the brain tone atlas in order to group the voxels of each brain area. Now the question is, how can we represent or group the voxels for each area? So we calculate a histogram of 6 values for each area. These values represent the percentage of the voxels for a specific area in 6 z-statistical levels. So the first value is the percentage of voxels in that area that have z-value between 0 and 1, 1 and 2, 2 and 3, 3 and 4, 4 and 5, and more than 5. So now we have 246 brain areas, each having 6 values, which represents our feature vector. In the third step of our framework, which is the classification and severity grading, we input our feature vector of 246 by 6 values to further feature elimination, using recursive feature elimination with the random forest classifier. This step outputs a reduced feature vector. We input the feature vector to different classifiers. We have tested the random forest, support vector machine, and the multilinear perceptron with different hyperparameters. The best performing classifier is the random forest. A quick recall on our dataset. We have adopted a dataset of 39 subjects, each group having 13 subjects. We use random forest classifier in both the recursive feature elimination and classification. For testing, we use the tenfold cross-validation technique to calculate the accuracy of the classification. We have obtained an average grading accuracy of 71.79%. Table 1 shows the confusion metrics. We have performed the validation step to our framework. Since features represent areas, as each area has a histogram of 6 values, so if the recursive feature elimination selects these 6 values, that means that this area is a discriminating area. We have applied group analysis for each of the included 3 groups using FLAME, which is a tool in PhD that is used for high-level analysis. So we have validated the selected features by comparing them with the most activated areas in the group analysis using FLAME. As we can see in the figure, the orange highlighted areas are the activated areas obtained by FLAME. The other colored areas are the most selected areas by RFE. We can notice the overlap. Another way of validation is by sorting the areas in each group that has the high percentage of significant voxels. So table 3 shows the top 5 areas having percent of significant voxels for each group. Table 2 shows the brain areas having maximum selected features by RFE. So by comparing these two tables, we reveal the high intersection between the selected areas by RFE and the top activated areas in each group. So to conclude our work in this study, we introduced a machine learning based approach for autism severity grading on the autism spectrum. The proposed algorithm achieved average grading accuracy of 72 using random forest classifier with recursive feature elimination. We also applied group analysis to validate selected features and study colon group brain activation. It is obvious that our top RFE informative areas match the group analysis results. Our future work will focus mainly on integrating more fMRI data from different experiments. In addition, integrating different modalities such as structural MRI and DTI will give more comprehensive understanding of how brain activation abnormalities in response to different tasks explain autism. Such significant differences will be investigated to correlate with ADOS reports to develop personalized diagnosis and treatment. Thank you for your interest and for listening to our presentation. It would have been an honor meeting you. I wish wellness for everyone and for our loved ones. Please stay safe. Please feel free if you have any questions. You can contact me on my email. Thank you.